In this video, we're going to compute the integral of the cosine to the power of n of x from 0 to 2 pi for every natural number n. We have to consider two cases. N is an odd number or n is an even number. We will start with the case where n is odd, and we will need to use four properties. First, notice that the cosine to the power of n of x is a periodic function with period 2 pi. Second, notice that the cosine to the power of n of x is an even function. Third, notice that we can write the cosine to the power of n of x as a sine to the power of n with a shift in the argument. Fourth, notice that the sine to the power of n of x is an odd function. This only works if n is odd. Now we start with our original integral. And we apply property 1 to change the interval of integration, because if the cosine to the n has period 2 pi, then the integral is the same over any interval of length 2 pi. For example, it will be useful to consider the interval negative pi, pi. Now, by property 2, cosine to the n is symmetric with respect to the y-axis. So the integral over the interval negative pi, pi is just twice the integral over the interval 0, pi. By property 3, write the cosine in terms of the sine. Now we make a very simple u substitution. Consider u equal to pi over 2 minus x, and derive to obtain the new differential. Apply the change of variable to the integrands as well as to the limits of integration. You can use that extra negative sign to swap the limits of integration. And finally, we use property 4 to prove that this integral is 0, since the sine to the power of n of x when n is odd is symmetric with respect to the origin, and we are integrating over a symmetric interval. In conclusion, if n is odd, the integral of the cosine to the power of n of x from 0 to 2 pi is 0. Now consider the case where n is even. We start with our integral, and we are going to use the complex representation of the cosine. That is, in terms of exponential functions with imaginary exponents. Take the denominator out of the integral, since it does not depend on x. And now we multiply both the numerator and the denominator by I times e to the power of ix. This will make sense in a moment. The reason to do this is that we want to prepare the integral to turn it into a complex line integral. Recall the definition. Consider a function g that we want to integrate along a path L parametrized by the function gamma between the parameters a and b. Then, this complex line integral is given by the integral that you see on the right. So actually, we're going to apply the definition from right to left. We have a regular integral between 0 and 2 pi, and we want a line integral. Also, the theorem that we will use later requires a line integral along a closed curve. Given that our integral had many terms of the form e to the ix, a natural choice is the parametrization c equal to gamma of x equal to e to the power of ix between 0 and 2 pi, which corresponds to the parametrization of the unit circle L in the complex plane. Derive in order to obtain the new differential, and maybe now you can see why we wanted to have an extra term of I times e to the ix. Now the conversion is straightforward. Put e to the ix equal to c, e to the negative ix equal to c to the negative 1, and also substitute the new differential. Now expand the numerator using the binomial theorem. You know that you can write a sum of two terms to the power of n as a finite sum of n plus 1 terms. In particular, you see on the right the result of expanding the numerator with the corresponding products of the binomial theorem. And finally, if you put together all the terms with base z, including the denominator, you arrive at this expression, which is actually a Laurent series expansion of the integrand, since it is a sum of coefficients multiplied by powers of z with positive and negative exponents. Now we have finally arrived at the main theorem that justifies all the manipulations that we have performed in the previous steps. This is called the residue theorem, and it tells us a method to compute a complex line integral of a function h along a closed path L. So basically we have to consider that h may have m singular points a sub k, and there are two quantities for each singular point. One is the winding number of the closed curve gamma around the singular point a sub k, and the other one is the residue of h at the singular point a sub k. Multiply these two quantities for each singular point, add the products of all singular points, and multiply the result by 2 pi I. According to the residue theorem, this gives you the result of the desired complex line integral. In our case, we expressed the integrands of the line integral as the Laurent series that you see here. So this is our function h. Now, the function h consists of a sum of coefficients multiplied by powers of z. There is always at least one term with negative exponent for every even n, so c equal to 0 is always a singular point, and it is the only one. Since gamma is a positively oriented simple closed curve, the winding number is 1 if a singular point is in the interior of the curve, and 0 if not. The only singular point is z equal to 0, which is in the interior of the unit circle, so the winding number associated with our curve and the origin of the complex plane is 1. The residue of h associated with the only singular point z equal to 0 is just the coefficient that goes with c to the power of negative 1. And we attain that coefficient when the exponent of c satisfies that 2k minus n minus 1 is equal to negative 1. Solve for k, and you obtain k equal to n over 2. Now substitute k equal to n over 2, and you will get the value of the specific coefficient. In this case, the coefficients are of the form n choose k. So evaluating at k equal to n over 2, you get that the residue associated with the function h and the origin of the complex plane is n choose n over 2. Although it is now practically unrecognizable, this is our original integral of the cosine to the power of n of x from 0 to 2 pi for even n, which we have converted into this expression that you see on the screen after many operations. Now all we have to do is apply the residue theorem. So we have 1 over 2 to the n times I, which is the constant that we had at the front since the beginning, and the rest of the terms come from the residue theorem. We have 2 pi I times the winding number associated with the path of the unit circle and the singular point 0, times the residue associated with the integrand and the singular point 0. We already know that the winding number is 1, and the residue is n choose n over 2. Cancel out a factor 2 and cancel out the imaginary unit, so we arrive at a real quantity as expected. To sum up, the integral of the cosine to the power of n of x from 0 to 2 pi depends on whether n is odd or even. If it is odd, the integral is 0. If it is even, the integral is pi over 2 to the n minus 1. times n choose n over 2. And of course, if you wish, you may expand the binomial coefficient as n factorial divided by n over 2 factorial squared.